and a warm hello to all Clintel friends and colleagues and guests. While you take a look to the content, that's it. I would like to make a very short, brief introduction. Since the failed Kyoto Protocol in 2005, passing through Copenhagen and Paris until today's insane global reset and the net zero madness, Western governments have become increasingly hostile to and have openly declared war against fossil fuels, thus to the heart of the free market system, the essence of prosperity, whose first victims have been transportation and electricity generation. The global warming religion has tried to panic people with false beliefs that predict a catastrophic man-made climate change, where human CO2 emissions are to blame. With renewables, on the contrary, its priests have brought the new green gospel, successfully having seduced almost the entire free world political spectrum into the faith that they are clean energy sources, sustainable, most affordable, engines of development, and essential to avoid this tragedy because they don't burn fossils. Today we will lift the enchanted rug and see what is under these green wonders which will prevent the planet from a non-existent disaster. Starting by presenting the renewable showcase in which we are convinced that increasing renewable generation, then we will see a drop in price of electricity. I will come back to this graph because perhaps, only perhaps there's something hidden behind. But on the other hand, we have the facts coming from Europe and Australia, where by increasing the renewable generation, the price of electricity goes up, as well as in many, many other places in America and everywhere. And what about CO2 emissions? Well, it seems that thanks to renewable, CO2 emissions have dropped in Germany, in the UK, in Japan, in France. But again, isn't there something hidden behind this beautiful green graphs? Oh, yes, there is. In all those countries, electricity generation has come down. Now, anyway, this is not a proof that because of a drop in electricity generation, then CO2 emissions came down. Perhaps also thanks to renewables, because correlation does not necessarily imply causation, as you can see there. So we must go deeper in this, and we will see the benefits behind the logics with the green argument, which states that renewable energies are free since they don't burn fossil fuels, which is a true premise. And this other one that states that renewable costs have sharply decreased over the last 10 or 15 years, which is also a true premise. Then, conclusion, the cost of electricity must go down as well as CO2 emissions. But what happens when there is no relationship between cause effect? Then the conclusions derived from those premises become false and the entire argument becomes non-valid. So we must go deeper in the analysis, and for this purpose I will show to you a very simple and basic cost structure as an isolated system with a thermal and a renewable source with their technical and cost variables that lead to, someone has his microphone on, I believe, that leads to the levelized cost of electricity, which stands for the estimated revenue required to build and operate a generator over a given cost recovery period, and is the sum of the capital plus the fuel plus maintenance and operation plus transmission costs, among others I will not mention to make it simple. And as they use a common unit, they are useful and they are allowed to compare different cost variables within a generator as well as within technologies such as these ones. There we have the cost for the thermal and the renewable source of $40 and $56. So that's it, my friends. Goodbye. We're saving the planet and making electricity to go down. No, but perhaps, and only perhaps, there's something hidden here. What could be the grid cost of electricity, which we all pay for through our distribution company? That is why we must analyze a grid as an integrated or interconnected system, the definition itself of a grid. And what was missing here is this. What happens, for instance, if we increase the renewable generation in the grid? The thermal generation must necessarily go down because at every single moment, the total generation must be equal to the demand. Otherwise, we would be playing with a variable that is called the electrical frequency. And if we fool around with that variable, we blow the grid. So we can't do that. And besides, when the thermal generation is being reduced, its fuel cost increases because a larger amount of inefficient thermal generation will be needed to back up the natural intermittencies coming from renewables, as well as its fixed cost, because as the renewable generation increases, all the thermal costs will be distributed in a smaller amount of generation. So the cost of, sorry, I forgot the main issue here is the merit order. It's this little thing called merit order is defined as, it's an economic concept that means that in every moment, the grid will select the generation source that exhibits the least marginal or variable cost, in this case, the fuel cost. And for that purpose, renewables always have the least because their fuel cost of generation is zero. That is why in having dispatchable electricity, renewables will be always selected over other sources of generation. So the real cost of generation is not $40, it's not even $56, is 66.4. And why is this? Because the thermal cost of electricity went up to 77.7. And that is the other part that we are not told, they don't like us to know, and this is a cost that everyone pays for. In the absence of renewables, we only have a thermal source with a base load and a non-base load, which is the usual generation, inefficient generation for peak and off-peak demand, where the total generation or demand will be equal to the thermal generation that will be equal to the base load plus the non-base load generation. But in the presence of renewables, the situation changes a lot because we now need, as you can see in the dark gray stripe in between, we now need an inefficient fraction of the thermal generation to back up renewables. Now, the renewable generation can vary from generating at full load capacity, which invites us to believe that in that moment there's no need of backup generation. Fourth, every time we need, in this moment, where the renewable generation is operating at full load capacity, the entire fraction, the green fraction you see there, in the thermal source will be at idle, standby, burning fuel without generating electricity, waiting for the sun or the wind to go away. You can't turn off a thermal source like you turn off a light bulb or something like that. You can't do that. And in the other extreme, we have that the sun and the wind, they sometimes go away. And in that case, we will have all that stripe there destined to replace the lack of renewable generation. And this is very important because this indicates that we can't phase out or dismantle the installed capacity of the thermal source belonging to that thermal generation that we are not generating anymore because renewables came in. We can't phase them down. We must keep them for backup purposes. And in average, in a year average, that non-base load generation will be equal to the the renewable generation. That does not mean that we are increasing the thermal generation. No, we are just replacing a fraction of the thermal generation by inefficient thermal generation. We are not increasing it. And now we come to the first rule of thumb. If we demand stability in a grid, for every for every megawatt hour of renewable generation, there must be at least 1 megawatt of thermal capacity for backup. Now, this is how renewable advocates likes to show us the cost of electricity from the generator perspective, which is true, but it's half the truth. Let's suppose for a moment that there is a limit for the maximum renewable fraction in a grid beyond which all electricity in excess will be lost because we cannot inject more electricity to the grid than the one demanded. Between zero and that maximum, the cost of a renewable generation will be constant. Why? Because of the merit order. As we increase the installed capacity, all the renewable generation from that capacity will go into the grid. But beyond that maximum, it will start increasing. Why? Because if we continue to increase installed capacity, all the costs will be distributed in a constant generation. The thermal generation starts increasing right from the beginning because the fuel cost as well as the fixed cost rise as the renewable generation increases and stays constant beyond that limit because there's no further increase in renewable generation, thus no further reduction in thermal generation. Now, you may say I've been a bit misleading here because I put a renewable cost of generation greater than that of the thermal source, which renewables say is the opposite. Okay, let's put then a renewable generation cost lower than that of a thermal source. But that doesn't matter. What matters is the cost of electricity of the grid. And that one always increases no matter what, no matter how much we reduce the levelized cost of electricity of the renewable source. It will always increase, but even worse, it starts growing from the beginning. It goes up, not down, as renewable advocates try to convince us. And besides, it starts at the same level. That's the important thing. So again, there we have the renewable cost, which is not the cost that we pay for. There we have the thermal cost, and there we have the grid cost of electricity that is much greater because the thermal cost of electricity went up. In this case, in this exercise, we considered a 30% of renewable fraction, that is a 70% of thermal fraction in the grid, with a levelized cost of fuel of $4.6 per mega BTU. Now, seeing from the grid perspective, and here things starts to be a bit more complicated, so I will try to slow down a bit, so for me not to stumble with the words. This is the levelized cost times its generation fraction in the grid. Okay? It starts increasing from zero onwards. And this is a thermal weighted cost of electricity that, oh, surprise, it came down. Why is this? Now I have to introduce a new element here that we call the inefficiency factor K, about that says K lower than 2. This is defined as a ratio between the non-base load to the base load operating heat rate. This is the same as to determine the fuel consumption of your car driven in a city, including the fuel consumption or burning fuel that you incur when you are in a red light when waiting for the green light, to the fuel consumption rate of your same car driven in a highway at a constant speed, let's say 90 kilometers per hour. Then when K is lower than 2, then the increase in the fuel consumption is not able to cancel the effect of reducing the thermal generation, making the thermal weighted cost to slightly drop, and it remains constant beyond that limit. While the renewable generation increases, the other one slightly decreases. Thus, the effect of reducing the weighted thermal cost of electricity is not able to offset or to cancel the increase in the weighted cost of the renewable source, making the grid cost of electricity to inevitably increase. The dashed blue line there represents the cost of electricity without renewables. Now, this is the best case scenario when using as backup natural gas in combined cycle gas turbines. In no other thermal generation source, we will find that the weighted cost of electricity of the thermal source will drop, because when K is greater than 2, meaning that we also use simple cycle gas turbines, oil, or even coal, as in the case of the United States, the thermal weighted average will increase, will be positive, making the total grid electricity to be even greater. And now again, we have those costs that we saw, and we, in this case, can add directly the cost of the renewable thermal sources because they are already weighted cost. That gives you the $66.4 per megawatt hour above. Now, the fuel cost of electricity is defined as the unit cost of electricity in dollars per mega BTU times the operating heat rate in mega BTU by megawatt hour. That's the definition. Now, just in case Helios or Zephyrus decide to go away and leave us without electricity for a while, something that never happens, of course, because renewables are so stable, the question is there any backup alternative to combined cycle gas turbines? Yes, there is. If you see the left table there, I will refer only to simple cycle and oil power plants because the other I won't refer to nonsense. In those cases, yes, they're well suited to backup renewables. However, K factor or the efficiency factor K is greater than 2, making that the weighted thermal source cost of a thermal source will go up instead of down, as well as CO2 emissions, as we will see later. CO2 emissions also goes up with simple cycle and oil generation. So we always come back to combined cycle. And in the right table, in the non-suitable sources of generation, coal, biomass, and geothermal, they are simply too slow to react on time to sudden weather variability. As I like to say, turtles and rabbits just run at different speeds. And also coal and biomass have a K factor greater than 2, making that the thermal weighted cost as well as CO2 emissions will go up as the renewable generation increases. Renewable advocates, when they state that the costs of renewables have gone down for the last 10 or 15 years, they refer to the investment cost of renewables. And the investment cost is not an electricity cost. That is the trick behind what they state, because it's in units of currency to power, while the capital cost is in fact a cost of electricity, which is in units of currency to energy, megawatt hours. While the capital cost is proportional to the investment cost, it is inversely proportional to its capacity factor. And the capacity factor can range between 2 to 6 times greater than that of a renewable source. Now, how we turn the investment cost into a capital cost. There you have the equation for the annual payment of an investment when you ask for a loan in the bank, where R in this case is not the market interest rate, but is rather the weighted average capital cost, which is used in large investments in large companies. If you are interested in knowing more about weighted average capital cost, you may go to the document that will be sent to you soon after this presentation. Now, dividing the annual payment by the maximum generation of 1 megawatt of that investment is what gives us the capital cost. And as you can see there, it's inversely proportional to the capacity factor Z. Now, seeing this from a graph, the horizontal axis shows the ratio between investments, and when that ratio is equal to 1, that means that the investment costs of the renewable and the thermal source are the same. For instance, $1 million per megawatt of investment or installed capacity. In that case, the capital cost of a renewable source will be almost 3 times greater than that of the thermal source, with a capacity factor of 30%. But if we reduce the capacity factor to 0.2, it will be more than 4 times greater. And that is a big trick, because it's the part that they don't like to show us. The capital cost is what matters, and not the investment cost or the cost of renewables, as how they say. So finally, no matter how low the renewable investment cost may be, its capital cost will still be much higher than that of a thermal source. Remember this graph? Well, I will tell you where's the trick here. It happens to be an overlapped graph, and the drop in electricity price is not because the increase in renewable generation, but rather because a big drop in Brent oil price, as well as the price of natural gas. There you have it. This is very important, because we must know if there is in fact a limit to renewable generation on any grid. And yes, there is, and well defined. Well, I will start explaining this with a little simple algebra, high school algebra, and then I will go to a graph, just in case I'm not able to explain it well. Let Q be the installed and enabled capacity in megawatts to satisfy the demand W, or annual generation, which is the same, and let D be the hourly demand in megawatt hours per hour, or megawatts. Okay, that's the equation, very simple. And now let N be the installed capacity to satisfy the fraction F of the annual generation. That will be F times equation 1. Clear up until now? Now, which is the condition to be at a limit? Is that the installed capacity, let's talk about renewables from now on, the installed renewable capacity must be able to match the hourly demand. In that case, it's easy to understand if I increase the generation, that extra generation will be necessarily lost. So that is the maximum. And if we replace N equals D in equation 2, we immediately get that F max, or the maximum renewable generation fraction in a grid, is equal to its capacity factor. This is revolutionary, as well as so simple, because it has been a lot of discussion about this, and it can't be more simple. Now, going even further, we can define now Q as a penetration factor, that is the nameplate capacity divided by the hourly demand. In this case, the condition for being at the maximum renewable generation fraction is that Q will be equal to 1. And this beautiful equation here, only the genius of someone like Lord Monckton could have come up with a name like this. For the excess generation E equals N minus D, and the N for renewables. Hopefully. And there you have the two main equations. And now we can explain this with a graph. Let's suppose that we have a renewable generation fraction of 15% with a capacity factor of 25%. That means that there will be moments that installed capacity operating at full load will be able to generate up to 60% of the hourly demand. If we continue to increase the renewable generation fraction up to 25%, making it equal to its capacity factor, then there will be times that the renewable source operating at full load capacity will be able to satisfy 100% of the hourly demand. And it's easy to understand that beyond that, all extra generation will be necessarily lost. Now, here we have the situation for 11 nations. This is no surprise. Germany has been number one for a long term. And the four countries below, Japan, France, USA, and Brazil, they still have some room to add renewables, to spoil their grids, to make electricity along with the others, to increase and to damage their economies. But however, they still got room. Now, let's go to CO2 emissions. This is the same analysis as for the electricity cost of generation, because the operating heat rate is related with the now what we call the output CO2 output emission rate E. 0.06 times H equals E. If you want to ask me afterwards, where did I take that 0.06, you may ask me. So, when K factor is lower than 2, then the increase in CO2 output emissions rate is not able to cancel the effect of reducing the thermal generation, making the CO2 emissions of the thermal source to slightly drop. And this is the only case that we can obtain and get and achieve some reductions in CO2 emissions by using natural gas in combined cycle gas turbines. In no other thermal source we can see that. Using simple cycle oil or coal, it will make that the increase in CO2 output emissions rate this time will be able to cancel or to offset the effect of reducing the thermal generation, making the CO2 emissions of the thermal source to increase. And that is the case for the entire world, except for 3 or 4 very exceptional cases, and you can ask me afterwards why. Now, in the absence of renewables, we have that the thermal generation is equal to the base load plus the non-base load, and the emissions, capital E, will be equal to the CO2 output emissions rate, lowercase e, times the thermal generation. Now, the output emission rate can be obtained from 2 different sources. At the left hand is available in every grid around the world because all the world signed the Paris Agreement, so we know how much CO2 emissions come from a thermal source and we know its generation. So dividing one by the other, we immediately get the CO2 output emissions rate. But we can also obtain it as a weighted average, weighted by their respective base load and non-base load generation. Now, in this right side of the equation, which would be the only unknown variable, omega n, the CO2 non-base load output emissions rate. Only if we are able to know the base load and non-base load generation. If any country is able to show or divide the total thermal generation into base load and non-base load. Otherwise, this equation can't be solved because we will have one equation and 3 unknown variables, infinite solutions for each one of them. Now, omega B, the base load CO2 output emissions rate for combined cycle is well known because it's dividing 0.205 by 0.58, which is the efficiency of a combined cycle gas turbine facility operating at 95% of its full load capacity. And that gives you 0.353 tons of CO2 per megawatt hour. So the only missing variable or unknown variable is omega n. Now, if we are able to calculate omega n, problem solved, because in the presence of renewable, the equations for the output emissions rate is exactly the same as the one above. Instead, in this case, we must add only the non-base load generation to back up renewables plus the rotating reserve fractions, which I will now, will now explain. If you can see my laser below at the right, there we have R rotating reserve fraction equals G0 omega 0 times the non-base load renewable thermal generation to backup. G0 is the percentage of the full load capacity of a thermal source operating at rotating reserve or in idle, burning fuel without generating electricity, and that ranges between 5 to 7% of its full load generation. And omega 0 is the base load CO2 output emissions rate, this time of a simple cycle gas turbine. And why not combined cycle? Because at rotating reserve, the combined cycle gas turbine long before left aside its steam booster and is operating at that operating level as a simple cycle one. So now we can see what is going on in the United States. If the United States for the year 2021 would have only used natural gas to back up renewables in combined cycle, then they would have achieved a 5.3% of the country's CO2 emissions compared to the grid emissions. But it happens that the United States also uses oil, gas, simple cycle gas turbines, and even coal. So in fact, the real reduction in CO2 emissions was only 0.7% with respect to the grid. And this is all attributable only to renewables. Because in economics, we call this ceteris paribus. In calculus, in thermodynamics, we call it partial derivatives, leaving all the rest aside, what will not interfere with this system. So in the case of the United States, they only achieved 0.7% thanks to renewables, 0.2% with respect to the United States total emissions, and 0% with respect to global emissions, meaning that the second largest emitter in the world, the planet didn't notice their efforts to save the planet with a 12% of renewable generation fraction, which, by the way, is useless because the real renewable generation fraction that we must consider is the one calculated as the total renewable generation divided by the total renewable generation itself plus the thermal generation that will be eventually used as backup. So that makes that the real renewable generation fraction increases up to 23.6%, dangerously close to the maximum limit of renewables for the United States to its capacity factor, which is 37.7, after having spending hundreds of billions of dollars, if not trillions, to achieve nothing. The world is not being saved by the United States. So, this is a case when we think about going from from coal generation to renewables using any kind of backup generation, compared to the situation from going to coal directly to natural gas generation. The table above will show you the first case when we only use natural gas for backup in combined cycle power plants. This means that going from coal to renewables using only natural gas as backup, instead of going directly from coal to natural gas without using renewables, will achieve 21% more of CO2 reductions. And in the second row, it shows the same, but in this case, with the use of all kinds of fuels, such as oil and even coal. In this case, going from coal directly to natural gas generation will allow to reduce CO2 emissions 91% more than going from coal to renewables, using all kinds of fuels to back up those renewables. And in the bottom table there, I show the figures for you to be able to calculate the above table. Now, conclusions. By increasing renewable generation, the cost of electricity inevitably increases regardless of any improvements from renewables, such as a reduction in their investment costs. The only way for the cost of electricity to drop by increasing renewable generation is for its investment cost to be close to zero, and at the same time, for the inefficient backup fuel consumption to be lower than that of the efficient operation, simply something that does not exist. It's the same as saying your fuel consumption car driven in the city has a lower consumption than the same car driven in a highway at a constant speed. We haven't still invented an engine like that. However, this is the least electricity cost increase and the basis of far larger hikes coming from policy spheres such as capacity payments and constraint or cancel generation orders, also all functions of renewable generation, but however, all costs of an electricity that does not exist. In ideal grids, a major CO2 emissions abatement can be achieved, therefore making renewables economically ineffective for this purpose. But in real-world power grids, where regeneration technologies other than combined cycle and/or fuels other than natural gas are also used as backup, CO2 emissions significantly rise, making renewables, apart from increasingly expensive, an irrational solution for the same purpose. The best way to reduce CO2 emissions, if needed, which is not, is by getting rid of renewables and going directly from coal to gas generation. There is a fundamental limit to renewable generation, which is equal to its capacity factor. Replacing coal by renewables hinders CO2 emissions, as we just saw, and the big West mistake. Asymmetric renewable expansion by decommissioning fossil fuels-based power plants without consistently increasing backup gas-fired generation capacity. And this is being an increasing problem all over the West. And finally, the net zero, an insane utopia trying to become true. Unlike China and Russia and India that have enriched themselves at the expense of the so-called free world, Western governments desperate to reduce CO2 emissions are compelling their nations to take the energy transition flight to wonderland in net zero, putting decarbonization before affordability, reliability, and energy security, at the end only to fail in all four, yet leading towards an economic breakdown, to the loss of sovereignty, and to the end of freedom. In addition to making electricity increasingly expensive and unstable without any impact on the climate or its changes, and to upsurge what was meant to be reduced, the West is beginning to painfully face the consequences of its disastrous mitigation measures, dangerously compromising electricity supply, which this civilization, our civilization, is based and completely depends on. Meanwhile, over the last 6 years, for every 1 terawatt-hour of coal generation capacity decommissioned in the West, 2.2 terawatt-hours of that same capacity has been added in China and India. Net zero, the world's first cool grass, is physically impossible to achieve for electricity generation as well as for any other activity. Nonetheless, the new architects of humanity are carrying mankind meekly to that green paradise just 20 years away. However, the West is already facing today the consequences of the colossal lack of rationality and vision of its governments that will take years, if not decades, to repair if there is any will to do so. going to net zero, but after entering a global economic collapse, is going into a global blackout that will only bring devastation and death. And when having just slightly pushed forward this deranged and genocidal extreme climate policies in the name of saving the planet from a non-problem as a last resort for survival, violent riots and coups will arise spontaneously, followed by civil wars, if not wars and invasions. Aren't the first two already happening? While the climate, immutable, follows its natural path by itself, the negligence of Western leaders and the evil of a few, none elected by no one, are driving humanity to a new stone age from where a few survivors will probably come out of their caves and huts on January 1st, 2051 and ask themselves naively, hasn't it all been in vain? Before saying goodbye, I must deeply thank to the many Clintel and Chilean engineers involved with the generation industry for their invaluable support, and especially to Professor Fred Udo from the Netherlands, who lifted me out of a black box almost 2 years ago, and to Lord Christopher Monckton from the UK, who has been by my side since the very beginning. Now I can say goodbye, and that is all, folks. Thank you.
First of all, let me thank the organizers for including me in this event. As an American, I don't want to presume to tell people in Ireland what they should or shouldn't do, but we are all facing the same issues, and it seems to me that sharing our experience and our thoughts has some value. Before I talk specifically about offshore wind, a couple of points of context. First of all, people in the West have gotten obsessed with the reduction of carbon dioxide emissions. And I'm very puzzled by this because carbon dioxide is in fact a benign molecule, which is essential for all life on Earth. It is not pollution. It doesn't make your air dirty. It doesn't make you unhealthy. And despite what Vice President Gore says about the vast amounts of CO2 we pumped into the atmosphere, it's in fact a very small amount. CO2 concentrations in the 1800s were about 0.03%, and now they're about 0.04%. And in fact, this is having a largely beneficial effect. The NASA satellite programs, and you can find this online, show a distinct greening of the Earth because carbon dioxide has a fertilization effect. It promotes plant growth and drought resistance. And this is particularly important if you look in places along the Sahara for people who are desperately in need of food. If we go back to the beginning of the climate change argument, the basic argument was that these amounts of CO2 that we put in the atmosphere would in fact bring massive increases in the temperature, which would in turn cause terrible disruptions to the climate. And those predictive massive increases, 4, 5, 6 degrees C, have simply not materialized. What we've seen is only about 1 degree Celsius in the last 120 years, consistent with a very modest kind of warming you'd expect from carbon dioxide. Now, the climate does indeed change, and we should all understand this, but it changes for a number of reasons. There's changes in the solar fluctuations in solar energy. There's slight changes in the Earth's orbit. There are volcanoes. There are clouds. There are long-term changes in ocean current systems. And of course, man-made carbon dioxide. But we don't understand any of these very well, and we certainly don't understand all of them put together. In fact, climate is too simple, is too complex for simple answers. Now, okay, what about all these weird weather events we've been seeing, heat waves and fire and drought and floods? Well, if you take any one of these things and you do a simple historical statistical analysis, you will find that all these disasters we are experiencing are within the range of natural variability. They are not, in fact, getting worse. Disaster predictions are artifacts of computer models, and these computer models are not capable of making useful predictions as yet. You cannot model what you do not understand. So my conclusion here is that there is no climate emergency. Now, you can agree with me or disagree with me, But if you disagree with me, there's still one more problem that you need to confront, and that is, where does the CO2 come from? Douglas made this point a few minutes ago. This chart shows the change in annual CO2 emissions in the EU and North America between 2000 and 2022. And as you can see, at great expense, hundreds of billions of dollars, there's been a modest decrease over 22 years. Now, while we've been focused on this, what's the rest of the world been doing? Well, the answer is this. China has more than tripled its emissions. India has more than doubled its emissions. And the rest of the world keeps on happily using fossil fuels and emitting CO2, regardless of what the West wants them to do. Now, the Paris Climate Agreement is currently in its 8th year, so we might expect some change in this trend, but the latest projections say no. The latest projections indicate that, again, at great expense, the EU and North America will make very small reductions in their CO2 emissions, and the rest of the world will continue to increase. I find it interesting on this chart that by the year 2030, India is emitting more CO2 than the European Union is. Now, we know that Ireland is a small country, but the Irish government constantly talks about its obligation to meet the EU directives. But the EU currently accounts for less than 8% of global emissions. As a result, EU climate policies have no material impact on global atmospheric CO2. So what we're really left with is the question of the economic cost of producing electricity in different ways. Now, Douglas addressed this problem by looking at the overall grid and the problems that occur when you try to use both renewable and thermal electricity. I have come to exactly the same conclusion he has, but I've done it through a different mechanism. I've looked at this problem as an investor thinking about building an additional power plant. And my conclusion is that offshore wind is expensive, it's intermittent, and because it's intermittent, it's unreliable. I don't agree with those climate activists who claim that wind power is inexpensive. I think it's in fact very expensive. And let me show you my calculations. Before I do that, let me just mention Ireland currently is basically running its electricity system on natural gas with increasing amounts of wind. There's a little bit of coal at Money Point. There's some oil and hydro and other, but this is really a choice between wind and natural gas. Now, let's think about an investor thinking about building one additional power plant in Ireland. If we talk about an 800 megawatt natural gas combined cycle power plant, the capital cost of that system would be about 735 million euros. It could run as high as 85% load factor. It doesn't have to, but it can. And with a 30 euro per megawatt hour fuel cost, it could generate 6 million megawatt hours a year, and it could generate them when you want them, not just when nature gives them to you. Now, by my calculations, if you could sell that electricity for 70 euros per megawatt hour, you could cover all your capital and all your operating costs, fuel costs, and still give your investors a return on their investment. Now, suppose as an investor, I look instead in isolation at building a comparably sized offshore wind farm. Those 800 megawatts would cost over 4 times as much, 3.3 billion euros, and they could only operate at best at a 45% load factor. That's the number used by the Electricity Supply Board. It seems to me a bit high, but let's just take it as it is. There's no fuel cost, but it would only be capable of producing 3.2 million megawatt hours a year. So the absence of fuel cost doesn't nearly make up for the high capital cost. And this would require 125 euros per megawatt hour to give you a return on your investment and cover your other costs. But I can't do that because you can't operate such a plant in isolation because it's intermittent. So let's suppose as an alternative, I think of building both plants, and I'll use the offshore wind farm whenever I can. And when I can't get wind electricity, I'll use the backup natural gas combined cycle. Now, we save some fuel costs on the natural gas plant, but you still have to maintain it, and you still have to give your investors a return on investment. So for this combined system, my estimate is that you'd have to sell that electricity at 107 euros per megawatt hour, which would cost you an additional 210 million euros per year for your 6 million megawatt hours. Now, you can do several things with that. You can pass that along to the consumer. You can subsidize the natural gas plant to keep it operating, or you can not have a natural gas backup plant, in which case, as Douglas explained, you'll have a not only very expensive, but very unstable and unreliable grid. Now, my summary calculations show that for Ireland as a whole, currently generating about 35 million megawatt hours a year at an average wholesale price of 105.5 euros per megawatt hour, which is a total value of 3.7 billion euros. It makes a great deal of difference to the Irish economy, how much that electricity costs. Now, if we're talking about adding, theoretically, an additional 6 million megawatt hours, if we do that just by natural gas combined cycle, that would be 430 million euros a year. The combined offshore wind and natural gas combined cycle would be 640, or an additional cost of 210 million euros. Now, that would save you about 1 million tons a year of carbon dioxide. In other words, about 210 euros per ton. Now, is that a lot or a little? Well, just points of reference, European carbon market price is 85 to 90 euros per ton currently. And the US social cost of carbon, which is not a market price, but is the standard set by the US government for measuring whether carbon reduction steps are worthwhile, is only $50. So by my calculation, using offshore wind will cost you about 4 times as much, 2 to 4 times as much to reduce carbon dioxide as it's worth. Now, a few additional issues. This is not a full cost analysis. There are other things involved. There's the carbon that's involved in making the units. I haven't included that here. There are additional interconnection and grid management costs, which Douglas outlined. Wind turbines do tend to degrade over time because the blades are scoured by dust and bird strikes and other things like that. There are quality control issues. There have been major recalls lately for the turbines built by Siemens Gamesa and Vestas. There are supply chain problems currently leading to delays, and there are environmental issues. In the United States, we find that every time you try to build one of these things, there's a lot of upset among the environmental groups about the effect on marine mammals and so on and so forth. So my conclusion is that CO2 mitigation through offshore wind farms is very expensive, but most of all, it carries no benefit. And it would seem to me that natural gas is a much better option for Ireland. It's clean, it's much less expensive, and there's a global LNG market that's growing rapidly, becoming much more flexible and giving smaller countries much greater opportunity to access this low-cost fuel. There's a great deal of natural gas in the world, and it seems to me the best strategy is to take advantage of that. So basically, Douglas and I approached this problem from different perspectives, but I think we reached the same conclusions.